Thanks. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just pray that you'd help us to use this time wisely, Lord, to glorify you in what we do. In your name I pray, Lord Jesus. Amen. Let me just take a couple minutes to talk to you about symmetries. Won't take too long. So, you guys had a homework problem where you showed that if you look at a subset of permutations that fix a set, right? If you look at, say, we look at Sn, we pick x as a subset of the numbers from 1 to n, right? And then we look at all permutations which just fix the set x, right? That formed a subgroup. It was one of your homework problems, right? This idea generalizes, and you can talk about the symmetry group of some geometrics figure. So here's a definition for my 2016 notes, because I mean, section 2.7 in Nicholson, not bad, but there's something missing there, and I'm not going to fix all of it today. But I'm just going to get the ball rolling. Really, just wanted to throw this out here for you. So if we have, say, omega is some subset of R2, all right, then the symmetry group of omega is denoted, in fact, defined, sigma. It's like summation symbol of omega. And what that's going to be is just phi in the isometries. So you've worked on these guys, right? Isometries of R2 such that, guess what? Phi of omega is equal to omega again. So in section 2.7, Nicholson describes a symmetry of some like collection of points, and he says a symmetry is it's some mapping on the points which preserves the distance between the points and maps the same set of points, something like this. And then he makes a distinction between like a symmetry versus a motion. Anyway, so this is a symmetry group of a figure, and so let me just look at a specific example of this. We'll come back to this idea later. I just want to introduce the concept here. So maybe omega is just a set of 3 points, say A, B, C, right? And it could be like in the plane, these 3 points, right? So you could look at the set of isometries of the plane which fix these 3 points. So what would that amount to? What are isometries of the plane? You have some sense of this from that homework problem that you worked, right? You did it for Rn, I think.
Wait, was this for this class or advanced calculus?
This class, we had didn't we have this class?
I know we did stuff for advanced calculus.
It was in here. You suffer from the same confusion I do, being in both worlds, but I think in here we proved that an origin fixing isometry of Rn is necessarily linear.
You're right.
An experience you should remember as it was unpleasant.
Yes.
I mean, that's a hard thing to prove, actually. But that's the interesting thing, is if you're going to preserve the distance between points with respect to the Euclidean metric, you either have orthogonal transformations, those are the origin fixing ones, or you have translations. Of course, translations move the origin, right? Or you have composition of the two things. Compositions of rotations, reflections, and translations all together form what's called the group of rigid motions. Okay, so the group of rigid motions on the plane include rotations, reflections. Those together make the orthogonal group, which you studied in the homework, right? And then also there's translations. Compositions of these altogether give you the group of rigid motions. And that is what it sounds like. So a rigid motion is one which takes an object, a rigid object, and it moves it to that same kind of object. Like it preserves the shape of things. They're shape preserving maps. So here, I mean, what can you do?
You can rotate the thing.
Right. Maybe I should call this like 1, 2, 3, just to make it easier on me. So I can rotate it, right? We have a rotation.
So we're assuming it's equilateral.
Yeah, equilateral. Yes, indeed. If it was an isosceles, then we have less. So yeah, if it's isosceles, pretty much we can just flip those and do the identity transformation. So that would have a symmetry group, which is essentially just Z2, or C2 if you like. But here we have the rotation by 60 degrees, right? But we also have what? The what? Oh, okay, so we also have R squared. But how about this one? Right, we can also do this, right? We can flip. And we'd still get those same 3 points, right? So let's see here. The notation then. So we have R. We have R squared. Of course, we've got the identity transformation. You know, these are in the group of symmetries. There's also this reflection, right, which we could call Y. Or I guess I'm using, I don't know, what label do you want? We can't use R. What's that?
Mu.
Oh, mu. Okay, sure. Interesting choice. So what happens if you do mu 2 times?
Identity.
1, right? It's mu 2. Okay, so of course we have R cubed is 1, right? So geometrically you can experiment here, right? What happens? Let's think about this. We do the reflection and then the rotation. Or I'm sorry, the other way around. Rotation then reflection. So here's the starting point. 1, 2, 3, right? These pictures are very inefficient, but they're helpful for the concept to start with. So let me do it. We start with 1, 2, 3. We rotate. That gets us to what? Let's see what we got. Am I doing clockwise or counterclockwise? Oh, come on. Let's go counterclockwise. Let's not be weird. There we go. Better. So 2, 3 came up here. 1 came over here, right? That's my rotation. And then my reflection gets me where? 1 and 2 flip, right? 3 stays up here. So we could rotate and then reflect. Now, so this is, mu r, right? Thinking of these as permutations, reading them like composition of functions, right? Then on the other hand, we could look at, let's see here, how about if we look at R squared? Let's instead look at R squared. What happens if we do, I'm sorry, I'll get it right eventually here, mu to start with. Mu to start with, we go what? We got our 2 upstairs, 3 and 1 flipped, right? You got me? And then what happens if we then do R squared, which is a rotation by 120 degrees counterclockwise? Where does that get us to? Does it get us back to here? If I take this and I, what?
Very first rotation should 1, 2 the other way
You mean my middle black triangle's wrong?
I think so.
Okay. Phew. All right. So 3, 1, and then if I rotate, not once, but you see where I got to? 2 went to here, then went to there. The 1 went to here, then went to there. In other words, there. And the 3 moved up there. In other words, back here again. So I have geometrically shown you that reflection, rotation followed by reflection is equal to rotation squared. I mean reflection and then rotation squared. So this, let's see here, can we rewrite this? How about this is also, if we multiply what? Mu on the right side. Okay, so this is r is equal to mu r squared mu, among other things. I don't know, but the larger point is this is what I mean. The way I look at this is mu r is equal to r inverse mu. You may recall, like if we look at D3, right, which was generated by x and y, such that x cubed was 1, y squared was 1, and we have the relation, oh curses, how did I write it? I can't remember. Was it yxy equals to x? Inverse? xyx equals to y? I can't remember. Anyway, the point is, one of the close, I mean, the relation that I derived was that we get this, right? So that relation that when you pass the rotation past the reflection, it becomes the inverse, that's essentially equivalent to this condition, right? And so what I'm trying to argue to you is that this group of symmetries on the triangle is really what we call D3. Because it has 2 generators, it has a reflection, it has a rotation. The rotation has order 3, the reflection has order 2, and how are they intertwined? By the same relation as this guy. So there's an obvious isomorphism, namely the one that has like psi of x equals to r and psi of y equals to mu, your notation. This is going to give you an isomorphism from our abstract D3 to this geometric group of symmetries of the equilateral triangle. And so anyway, this can be generalized to looking at more vertices and such, but save that for some other day. I just wanted to throw that in there to make this D3 thing a little bit less mystical to you, because I've just introduced this. This is an example because it's got nice properties, it's fun to play with, but I haven't really said anything about its geometric origins, and this is the start of that discussion. That's all I want to say today, because I want to leave the rest of the time for you guys to ask me questions about the test. This is not on the test, right? It's just kind of the next thing on our list of things to do. And I said that you could, you can skip in the homework the one you're turning in Monday, before the test, obviously. You can skip the. I think there's like a token problem at the very end, maybe 2, right? 3, 2. Those 2 postpone to the next. What did I call it? Training mission. Okay, yeah. All right, that's all I got for now. So this, of course, is one of the other. I mean, to give you a bigger picture here, the group of symmetries of an object is very much dependent on what you determine are the isometries of your geometry. Isometries depend on your notion of geometry, your notion of distance between points. If you chose a different notion of distance between points, if you chose a different thing to preserve than Euclidean distance, then you'd come up with a different notion of geometry and consequently different notions of isometries, and different objects would be preserved under that geometry. Under Euclidean geometry, we preserve things like shapes, triangles, squares, things you know and love, right? And it's an interesting and rewarding program to try to classify the discrete subgroups of the isometries of the plane. If you watch the YouTube series by Professor Gross of Harvard, he spends about 3 or 4 lectures deriving the discrete symmetries of this. It's really interesting and quite subtle. And I've been tempted to do that in here, but the thing is, as beautiful as it is, I don't know how to get a single homework problem out of the whole thing. Like, it's just this like really long, intricate derivation, and then I don't have homework problems to assign from it. And it's not really supported by our book. It's from a different book, which I would not use. So, oh well. Advertisement, go watch it. Or don't.
Could you post a link to that in the
What's that?
announcements?
Yeah, sure. Yeah. That I can do. All right, with that, I will shut up. You guys have questions? Or no questions, let's just leave. What do you say? Yes? Oh, okay. Ah. How would that help? How about this? Do you guys have any questions about this homework you just turned in specifically? I'll have at least a partial solution up later today. I'm not sure if I'll get it all done today, but I'll try to have something up for you on this today.
Can we discuss number 9?
Number what?
9. Turning 20.
Oh.
20.
Oh, yeah, that one's easy, relatively speaking. So Q8 is basically, if you don't mind me using plus or minus notation, plus or minus 1, plus or minus I, plus or minus j, plus or minus k, right? Where these are quaternions, so they satisfy aha! Sorry, lost without my eraser. So these they all square to minus 1, right? Except what? Plus or minus 1, right? And so I hope you guys, well, I mean, I guess it's a little late to tell you, but we worked out some good examples of Cayley's theorem, which is basically this is to illustrate Cayley's theorem, right? So supposed to find a subgroup of S8 isomorphic to Q. So I have already destroyed my, I'm an idiot. So I need to actually list all 8 of them, right? So 1, minus 1, I, minus I, j, minus j, k, minus k. I need to do this so I can put an ordering. So I'm thinking of then this corresponding to the first thing, the second thing, the third thing, the fourth thing, the fifth thing, the sixth thing, the seventh thing, the 8th thing, right? And then if I look at left multiplication, basically Cayley's theorem is based on this isomorphism of the left multiplication operators in the group, right? So I need to study the composition of left multiplications and see where they go. They'll cycle back eventually. That tells me what cycle it is. Because the left multiplications are permutations, which means that they're necessarily, they're permutations on the group, which means that they permute the group elements. That means that if you pick one of those 8 group elements and feed it to left multiplication, it's going to go to another group element, right? Then you hit it on left multiplication again, it goes to another group element. Well, that corresponds under this correspondence to maybe 1 going to 4 or 1 going to 5 or whatever. So we pick one. Let's pick I, Li, and if you feed it if you feed it 1, right? Where you go? You go I. Feed it another. Hit it with I again. Hit the left multiplication by I again. You get I squared, right? Minus 1. Hit it again. We get minus I. Hit it again. We get minus I squared, also known as 1. Oops, my picture's wrong. We're back here again, right? So, what is that? Yeah, that's a cycle. That's what it is. It shows that these 4 group elements, 1, I, minus I, and minus 1, they're moved amongst each other by this permutation, L sub I. And let's see here. It's helpful for me to cheat in terms of like, this helps me. So this is the first one. That's the third one. And this is what's up for grabs, right? It's not unique. Oh, poor grader. Oh my gosh, goodness, I just realized how awful grading this problem is. Whoa, it's truly awful. So in my current nomenclature, L sub I corresponds to the cycle 1, 3, 2, 4.
What about the other, yeah, there's a, you multiply by another just one cycle, right?
Oh yeah, that's just part of it. Yeah.
It's actually not as bad for the grader because they just have to look at the negative one. All the negative ones are going to be 2 apart in the four cycle one.
All the negative ones are 2 apart.
Because negative
L
one's
sub negative 1 is just
negative
4
one's going to be a whole
transitions.
bunch of disjoint 2 cycles.
Okay. I'm not disagreeing. I just.
It's going to be unique up to what they decided for.
Okay, so if you're like, how about L minus 1? That goes to minus 1, which then goes back again, right? So that's the transposition. What is this? This is 1 and 2. So L minus 1 is, in fact, corresponds to the transposition 1, 2. So
It switches all of those. So it switches a 3 to a 4 and a 5 to a 6 and a 7 to an 8 because they're all negatives of each other.
Right, that's the point, is that you're missing, L sub 1 is not, L sub minus 1 is not equal to that, it corresponds to that, it corresponds to, you have to take into account other elements, that's what it is. There's more than one cycle in L sub minus 1.
So if you start with a J, then acting on it by L minus 1.
all right, let's try this again.
Like if you go back to L sub I, try starting with J.
Oh, okay. So you're saying is fine. So L sub I is not done either, because L sub I can also start with something not in this list, right? So L sub I can start with J, right? And if we act L sub I on J, we get IJ, also known as K. And if we act on L sub I again, we get IK, right? Also known as minus J. And then if we act on by L sub I again, that gives us to minus IJ, which is what? K minus K. And then what happens? Then it goes back to J again. Okay. So that, thank you guys. I was tricked by my examples that I worked in the help session. I've forgotten this subtlety. I would have found it again when I worked the solution out. Not in front of you guys. 5. This is 5. This is 7. That is, what does it say? What did you say? 6. Okay, thanks. This is 8. So let's say L sub I includes. That's not all though, right? It also, and apparently, 5, 7, 6, 8, yeah?
L sub I is just the product of this.
Yeah, right. So 1, 3, 2, 4, 5, 7, 6, 8. This is one of the 8 elements in the isomorphic copy of this in S8. Let's see here, L minus 1. I think that one I can kind of eyeball, right? Left multiplication by minus 1 is going to correspond to, let's see here, 1, 2, 3, 4. This is what you guys are trying to tell me, but I couldn't see a minute ago. 5, 6, right? 7. This is what you guys were telling me, right? Yeah. I'm on board. Now you got Well, the identity's for free, right? That's in there. So that leaves us 5 more to go. I will post the solution. I hope that's enough to get you started. But the examples I did yesterday are considerably easier than this. Yeah. By the way, I think this has to do with the Cayley digraph of a group, which is something I have not covered, but it's really interesting. It's a graphical presentation of the operation of a group. You can draw a picture which illustrates all the multiplications in a group in a sort of systematic fashion. Yep.
Did you start with J on the like down there because the fifth element was the one not included in the original cycle?
Right. I could just as well have picked anything, any of the, anything not, any of these remaining 4, right? I could have started with anything else. And then, you know, I mean, this is, of course, the same as what? I mean, so that's, with my current calculational scheme, that would have been me starting with K. Did I do wrong? Or are you just giving me another one?
Yeah.
Oh, okay. 8576? Is that right? Why is that bothering me? I don't know. It's bothering me for some reason. Oh, you're fine. You're fine. Just let me not be bothered. Other questions?
Is the exam just up to 2.5 in the book?
Yes. Yeah. Yeah, I would not test on the 2.7 stuff at all. Except, of course, that I have included for you guys the example of the dihedral group, right? But for us, it's not a geometric example, right? So when I ask you questions about the dihedral group, do I expect you to answer them geometrically? No. I expect you to answer them algebraically, right? So, for example, you know, dn is what? It's 1x, x squared, xn minus 1. How's it go? Y. Did I do yx? I can't remember what my... What's that?
XY.
I do xy. I can't win for losing. Let's hear. It is the same thing, of course, yes, but I need to make a choice for the sake of discussion. And that's such that what? Well, okay, yeah, you get. Fair enough. And what? Xyx equals to y, right? So then for us, this is the dihedral group, degree n. Now, as a group, what's its order? 2n, yeah. So, you know, if I ask you to prove something like, you know, prove there are at least n elements of order 2, how would you do it? Right, we just take y, you know, x to the j times y x to the j, and we try to argue carefully that that has to be 1, right? Yeah, by induction, to be careful. If you already know my sneaky trick, if you already know my lemma, right, so prove the lemma, then we're pretty much good to go, right? I'll state the lemma in just a moment. So this is a lemma which is worth proving, as you said, by induction. So we can, this is a lemma you can prove. I'm sorry, I seem to have failed to. So that once you know that lemma, then everything is pretty easy to calculate in here, right? Because then this is so that shows that that has order 2 for arbitrary j. So there's n of those, right? J ranging from 0 to n minus 1. Now, why did I say there's at least n elements of order 2? There could be one more, right? What's the other thing? If n is even, right? For example, in D4, x squared has order 2 because x squared squared is x to the 4th, which is 1. But in like D3, there's only 3 elements of order 2. In D150, there is 151, right? Yeah. I guess we can talk about that now. Yeah. Suppose G is a finite abelian group with no element of order 2. Show that psi of G equals to G squared provides an automorphism of G. All right. Finite abelian. So what did we get? We're defining, our map is going to be psi of G is G squared, is that right? No? What? No? We're supposed to prove that that provides an automorphism given that G is what? Finite abelian group, no element in order 2. So no solution to G squared equals to E except what? G equals to E, right? It's number 28. Okay, so we need to show it's an automorphism, right? So how do you prove yourself to be an automorphism?
Homomorphism and then bijection.
Yeah, bijective homomorphism of the group.
In this case, you show it's injective, and then you say it's injective finite, therefore it's surjective.
Since it's, right, that's also a good point. Since we're in a finite context, we can either show onto or one-to-one. Either implies the other, right? Yeah, one-to-one is easier because if we can show it's a homomorphism, then if we can show the kernel is 0, that's essentially by definition. I mean, it's almost given to us here. But okay, so first of all, homomorphism is the first thing we should do because that's what's needed in order to apply the theorem that says that you can measure injectivity by the kernel, right? So GH is what? GH squared, but we're in the abelian case, right? So this is GH, which we can rewrite as GGHH, which is G squared H squared, which is psi of G, psi of H, right? Again, this is definition of psi. This is, definition of, square. And so, yeah, well, probably. I don't remember enough of the definitions at the moment to agree or disagree with that comment. But this much I know. This is abelian right here for sure. The fact that I'm not writing parentheses and writing 4 things means I'm using associativity. Fair enough. Generalized associativity, truth be told. So there you go. This proves that psi is a homomorphism. Then what? Then, like you said, if we look at the kernel of psi, this is going to be what? G in G such that psi of G is equal to E, right? But by definition, by assumption, there's no element of order 2, right? So if you look at this, this of course just means what? G squared equals to E. So the only way we can satisfy that is for G to be E itself. So it's clear then that this is just the set containing E, right? Which by our theorem means that that is, of course, well, that implies that psi is injective, right?
And then we showed in the training exercises that if it's injective and it's operating on a finite set, then it must be surjective.
Right. Psi is bijection, which implies, of course, that psi is an automorphism, right? So what's an example of the infinite? He says, give a counterexample in the infinite case, right? What is that counterexample going to be? You're going to use integers with addition? Very good. Yeah. Is that right? Integers with addition's not?
Yeah, because there's no n such that 2n
So let's say psi of x is equal to 2x. This is same as psi of g equals to g squared, but in the additive world, right? This is the additive version of that. So totally agree with you guys that psi fails to be onto z, right? Like psi of z is 2z. It's just the even integers. It's not the odd integers, so it's not a bijection. Consequently, not an automorphism. It is a homomorphism, though, right? Yeah.
Yeah, that's why that proof is nice, because it works all the way up until the very end where you use finite insertion.
All right. Yeah. Yeah. Does that help? Okay. So, guys, how would you prove the image of a subgroup is a subgroup? Here's a theorem. H is a subgroup of G, and suppose we've got alpha. I'm sorry, I need something a little more specific. Let's say H1 is a subset of G1, and alpha is a mapping from G1 to G2, right? I would claim is that alpha of H1 is a subgroup of G2. In other words, the image of a subgroup is a subgroup. Do you know how to prove this?
Is alpha homomorphism?
Yeah, I mean, yeah, there's alpha homomorphism. Sorry, I was about to say that, and then it got lost somewhere. Maybe the upside down. Here. Oh, at least one snicker. Okay, I'm just testing. Testing for viewership. Just one. Okay. Okay, so what do we do? Subgroup test, right? So notice that, first of all, what is alpha of H1, right? This is alpha of x, right, such that x is in H1. This is the image of H1 under alpha. So observe that alpha of E1, right, is equal to E2, where E1, I'm saying E1 is the identity in G1. I'm saying E2 is the identity in G2, just to be specific here. So that's the identity in G2, right? And of course, E1 is an element of H1, right? Because H1 is a subgroup of G1, hence what? Right, hence E2 is an element of alpha of H1, right? It's the image of an element of H1. So the identity is in the image of H1. Point number one. Now we should show it's closed, right? Let's show that alpha of H1 is closed. So let's say A comma B be elements of H1. Then there exist, let's say X and Y in H. Oh, I'm sorry. I don't want H1. What do I want there? I want H1 down here. What do I want up there? Alpha of H1. Thank you, guys. Because I'm trying to show that that's closed, right? Then there exist X and Y such that what? Alpha of X equals to A, right? And alpha of Y equals to B. That's just by the definition of image, right? Consider if we look at A times B, what do we got? right? Alpha of x times alpha of y, right? But alpha is a homomorphism. Man, I need to come up with a better abbreviation for that. Alpha is a homomorphism. I should just start calling them morphisms.
You just call it H and F.
Yeah. Anyway, but x and y in H1 implies that xy is in H1, as H1 is a subgroup of G1, right? Therefore, alpha of xy is an element of alpha of H1, right? Which is to say what? That is, AB is an element of H1. So we find H1 closed.
You mean element of alpha H1?
Yes, I keep doing that. Goodness gracious. I'll definitely take points off yours if you do that. So you can take points off my lecture today. I allow it. Right. Goodness gracious. Yes, if I could just focus for 3 seconds. Then we need to do what?
Inverses.
We need to show it's closed under inverses as well, right? Yeah. So, let's see here. Continuing, I'll continue to use observe. Let's see here. I always get hung up on the silly inverse part. Well, we know alpha of x inverse, right, is equal to alpha of x inverse, right? Which is alpha of x inverse by our early lemma on homomorphisms. But on the other hand, this is what? This is alpha of E1, right? Which is equal to E2.
If we're already using properties of exponents here, then we don't need all of this stuff. Like we can say alpha of x inverse equal to alpha of x inverse in 1.
Let's try that again. So you're like, okay, let alpha of x be an element of, well, let alpha of x be as before. Let's say, consider then a equals to alpha of x. So we're still assuming that this is the same a we picked before. And x is the point which maps to it. And then what?
So a inverse equals the inverse of alpha of x, which is equal to alpha of the inverse of x.
Aha, which is an element of alpha of H1, since x inverse is an element of H1, as H1 closed under inverses, right? Thank you. I have a penchant, I have a gift for making inverse arguments way more complicated than they need to be. It's one of my many gifts. But so like, you ever see me do an inverse argument and it seems awkward? Rest assured, there's a better way. It just didn't occur to me at that point. And like, there are ways of making anything in here more complicated. Like, you can always take the argument that's supposed to go from here to here and then like go out to the wilderness and wander around for 40 years, you know? It's very, very possible. Anyway, there you go. It's a subgroup by the subgroup test, right? Now, there's a corresponding partner problem to this, that the inverse image of a, right? We also have this corresponding theorem. If we have alpha, again, from G1 to G2, homomorphism. And if we have H2 is a subgroup of G2, then alpha inverse, the inverse image of H2 under alpha, is a subgroup of G1.
Don't you want isomorphism?
No, I do not.
But alpha might not be inverse.
It might not be inverse, but how do we know it doesn't inverse?
The inverse image does not require an inverse. This is set theory. Alpha inverse of H2 is equal to, what is it equal to? It is x in G1 such that alpha of x is an element of H2. Critical example of this, of course, would be alpha inverse of the set containing E2, right? That would be what? That would be x in G1 such that psi of x is an element of E2, right? But this is very silly. This is, of course, equivalent to the equation alpha of x equals to E2. And in fact, this inverse image has a name. What is this? Right, this is the kernel. So the kernel, of course, is the most important example of inverse image. And, you know, if we put H1 equal to G1 here, alpha of G1 is equal to what? This is the image of alpha, right? So special cases of these two theorems is that the image is a subgroup and the kernel is a subgroup as appropriate. But it's instructive to go through the proof. Again, it's a subgroup test theorem. But, you know, this one has a little bit more difficulty because, for you guys at least, because it's about inverse images. So you have to deal with the definition of inverse image and work through it. I can't do all of it. Let me just do closure for that one, and then I'll shut up about this. So let A and B be elements of alpha inverse of, what did I say? H2. Thus, there exist x and y in G1 such that what? Such that alpha of x equals to A and alpha of y equals to B. Did I do it wrong?
Yeah, because A and B are in G1.
X and Y should be in H2.
Oh, I'm sorry. I got it backwards, didn't I?
X and Y should be in H1. Or H2.
Process. So I want x, y, and G1.
X and Y.
Oh, these are supposed to be in G2, is your point?
Yeah. Well,
No, these are H2, right? Such that what? Alpha of A equal to x and alpha B equal to y. Have I now finally escaped my lecture-induced stupidity? No, maybe, I don't know. So then we want to show closure, right? So check it out. Let's see here. Alpha of A times alpha of B is what? This is alpha of AB, right? But it's also equal to, this is what? Right? Notice xy is an element of H2 since H2 is closed. Right? So the product of things in H2 is, again, in H2. And so what this shows is that the A times B maps under alpha to x times y. Consequently, AB is an element of the inverse image of H2. And that shows closure. Of course, course, to finish this, you need to think about inverse and the identity. But yeah. I think I proved these in the lecture after the one I posted last year, if you want to see me blather on about it for a half hour at a slower speed. See you Monday.